Good morning, good afternoon. Thank you for inviting me to deliver this keynote today. My name is Mehdi Bennis. I'm an associate professor at the Center for Wireless Communications in Finland. The topic of my keynote today will be about communication efficient and distributed machine learning for and over wireless networks. Here is a brief outline. So first I'll motivate Edge AI and the role it will play in beyond 5G and 6G. Then I'll present a number of techniques ranging from federated distillation, which is a novel technique for training models, different in nature than federated learning. Then I'll move on to talking about the genuine co-design between Edge AI and wireless communication. And then finally, I will talk about learning over random graph topologies as opposed to learning over star topology, which is in fact is federated learning. And then I will conclude and provide a few takeaways and also what's coming next. So let us start with some motivation. So the proliferation of intelligent devices and mission-critical applications at the network edge cannot be operated with centralized and best effort machine learning. On the one hand, these devices need to train their models in a distributed manner by communicating with other devices, either directly or via federated server over a capacity-limited links. On the other hand, these devices need to learn how to communicate in an ultra-reliable and low-latency manner under a number of constraints, such as small data, on-device constraints, network dynamics, channel dynamics, communication bandwidth, and so on. Communicating to learn while learning to communicate requires a novel machine learning and communication co-design, giving rise to a number of fundamental problems centered around communication efficient, low latency, reliable, and scalable model training, inference, and control. So everyone probably has seen this slide before, but essentially, traditionally, intelligence has been associated with the cloud. So this is what we refer to as classical AI, where the devices were basically transmitting their raw and private data to the cloud for training and inference. Recently, we moved on to the idea of federated learning, where here the idea is that the devices need to communicate not their raw data, but their models to the server, which aggregates them and then send them back. This has obviously many advantages in terms of privacy, bandwidth efficiency, and so on. And then, of course, the fully distributed setting where we get rid of the server. This is what we refer to. So to guide me through this talk, I'll be basically focusing on a number of techniques. So there is what we call the model parameter exchange. This is what federated learning does best, right? Where the idea is to transmit the models from the device or the server. Then you also have this model output exchange, where now you only transmit the outputs of your, say, neural network to the server, as opposed to the entire model parameters. And then a third one, which is not covered in this talk, which is surrogate data exchange, where you actually algorithms, right? And we'll start by focusing on the middle one here. So model output exchange, okay, and federated distillation. So what is federated distillation? So essentially, as I said before, I mean, here the setting is as follows. You have a number of clients here, right, or workers. So I'll be using this terminology interchangeably, but it essentially means the same. Then you have, of course, a server here, which would be a base station. It could be, I don't know, roadside units, a roadside unit, if these are vehicles or any other type of setting you may have in mind. And here the idea is that every worker here, as you can see here, has a own neural network here, right? And then, of course, what we said before is that this client will not transmit the entire model, but it will transmit the model output, which is referred to as a logit. So what is a logit, essentially? I mean, this capture here. If this is your input, this is your deep neural network, right? This is your softmax, typically, what you do to do the prediction, right, in a discriminative task. And just before this, you have actually what we call this output distribution, or the logit. So I don't know, for example, in a task classification problem of dogs and cats, this would be I mean, referred to as a kind of a histogram, right, where we give some, I mean, 20-80%, for example, here to the cat versus the dog. So this is exactly the information that we want to transmit in the uplink, as opposed to transmitting actually the entire model parameter, which will be, of course, very heavy in terms of payload, right? So this is the first intuition, right? Every device will store the local logit and then transmit this, I mean, transmit the local average logit per label, right, to the server, right? And then what the server will do essentially is just average
these logits, right? And then tries to now to distill them to every device. So every device locally will have essentially to perform distillation, we'll need to compare the prediction that it has locally, right, based on the data that it has, and essentially what the teacher here is trying to distill. So you compare two predictions, right? The teacher's prediction, right, and then the local prediction, and then essentially if the prediction between the student here, which is the client, and the teacher, which is the server, is very large, then you will actually try to use that as a regularizer in your model update. So this is what is actually given here. This is the weight update for the client I at say time k plus 1. Essentially, I mean, this is the previous weight update. This is the learning rate. This is the gradient of your loss function. And actually what is new here is this quantity here, which we add as a regularizer. It essentially quantifies the difference between the prediction made by the teacher, right? And the which is referred to as a global average logit, essentially, and then the local average logit, which is the student prediction. Okay, so again, the student prediction and the teacher prediction are compared, and then if that is actually, I mean, equal, then of course the student will continue with this weight, I mean, this learning update. Otherwise, it will add this regularizer to somehow push it towards in terms of using this as a regularizer in the learning. Okay, this of course will be then done either periodically, right, or as done here, or it could be done upon some other trigger rule. Okay, so essentially this is what is federated learning. I mean, the difference, of course, with federated learning is here we are not transmitting the entire neural network, right, which could be very large in the case of, say, I don't know, images, right, or other high-dimensional data, but just transmitting this output, which actually is much better in terms of communication efficiency, especially in the uplink, right, and then the operation here is to transfer the knowledge, I mean, or experience from all the other agents, right, via the teacher here, which is just basically averaging them, and then distilling them here, right, to the student or the client locally. So kind of it's also related a bit to transfer learning, although it's different. Okay, very good. So now mathematically, what federated distillation does, essentially, I mean, we have this optimization problem here for a given worker C, right? So this is your, I mean, empirical risk minimization, and this is a regularizer here that we, I mean, that we add essentially to quantify again the difference between the prediction of the local logit and the average logit, right, from all the other basically workers, right, and then we use this distillation regularizer in the learning. Okay, so this is essentially how the empirical risk minimization for federated distillation is written, right? And then this distillation regularizer, as I said before, will be this gap or knowledge gap that the student has, right? And then of course the teacher is there to essentially to help the student basically train faster, but also reach the same accuracy as the teacher. Okay, this is essentially what federated distillation does. So now let's take a look at, I mean, one application to see the gains of federated distillation compared to federated learning. So here we are in a classification task with the MNIST data set, right? And we assume, up to 10 workers. And here what we want to do is to compare the test accuracy, right, of federated learning and federated distillation, the number of devices. So what you can see here, of course, is that, I mean, if you focus here maybe on the IID case for now, so this is the accuracy of federated learning, right? And this is the accuracy of federated distillation. So you can see there is a gap here, right? There's a gap between this accuracy. So let's say that federated distillation has a slightly lower test accuracy, right? But what's more interesting is actually in terms of some communication costs here, federated learning, right, has a, I mean, two orders of magnitude higher number of costs compared to federated distillation. So this is to say that federated distillation actually achieves slightly lower test accuracy, right, compared to federated learning, but communicates much better, much more efficiently compared to federated learning. So actually there is a nice actually trade-off here, right? This applies to both, of course, IID settings and non-IID settings. Okay. So the takeaway here message is that higher communication efficiency is achieved with federated distillation, but at the cost of lower accuracy. So the question we would like to pose ourselves here is, can we do better, right? Can we actually somehow combine the benefits of federated learning and federated distillation? Because we know that federated distillation is very communication efficient, especially in the uplink, but federated learning maybe is actually better on the downlink. So let's see, perhaps we could. All right. Now we will actually move to another interesting aspect of edge AI, namely the co-design of machine learning and communication. So here we will see two different designs. One is referred to a digital versus the analog design, and see how actually that actually compares in terms of accuracy, scalability, and also energy. All right. So this is the focus here, right? So now when we say digital versus analog federated learning, what we mean by that is actually a number of things. So first of all, in the current literature, so the vast majority of papers essentially assume in the uplink, right, that every client will transmit its model, right, in an orthogonal channel or subcarrier, or maybe of course you can allow some interference to some extent, but if you really want to be within the federated learning setting where we have a very large number of IoT devices or clients transmitting their models, then for sure you cannot have orthogonal transmission. Okay, in other words, this does not scale across workers and model size. So of course now, how to avoid interference? Well, we know, from wireless communication, how we could do resource allocation, scheduling. You can even predict the channel, right, and then transmit the model after that. These are all valuable solutions, but can be limiting, especially in a very large setting. On the other hand, in analog setting, is different. Since in federated learning, the goal of the server is not really to decode the individual models, right? It's actually trying to decode the average model, all right? So in this case, actually, we could actually try to leverage maybe the channel superposition, right, through non-orthogonal transmission. Instead of doing orthogonal transmission as in the digital case, here we could leverage the channel superposition of this model updates and actually try to retrieve the average model, right? This obviously scales with the number of workers, because here, unlike the digital case where the performance will deteriorate as you increase the number of workers, right, because of interference on the uplink, here the performance gets better as you increase the number of workers. Okay. Not only that, it's actually much faster and much more communication efficient than the digital counterpart, and it can actually even provide privacy for free, because essentially here the channel superposition is playing the role of privacy in the context of, for instance, differential privacy. Okay. So here, instead of avoiding interference, we will harness it, right? And we will see that actually outperforms this digital federated learning counterpart. All right. So again, this is just the same thing visually. We have the digital federated learning setting here. The client, server. Again, of course, the client here will transmit their local over orthogonal band. So this could be over time or over frequency. Of course, you could do this over, space using multiple, MIMO, for instance, right? Whereas in the analog case, all the clients will use one, say, frequency, okay, or band to transmit all their models. Okay. So this is actually what is being done here. So to contrast both approaches, so here now what will happen is that every client will actually transmit a combination of its perturbed model. So this is the conjugate channel multiplied by the model plus some perturbation here. Or this is referring to the dual variable here that the client will transmit, and then the receiver will actually receive a combination of what the client transmit, plus of course some impaired noise here, what would be referred to also the fading channel, and then it will try to retrieve the average model based on this expression. Okay, this is essentially what is done in this approach. So of course we can formulate this mathematically, and this is what we actually done here. We can minimize, this empirical risk minimization here, and kind of encode the channel here within the model here. And then try to solve this using the ADMM technique. We can actually even prove that actually this algorithm converges asymptotically, where the sum of the primal and the dual residual converge to zero, right, as k goes to infinity. Okay, but what I want to really focus on here actually is a result. So first, in a linear regression task here, what we wanted to show essentially is how does this analog federated ADMM compares to the digital one, right, here in black, and also the digital baseline when I increase the number of carriers here by 10x, and also another baseline here in the analog gradient descent. Okay. So this is the loss versus number of communication uploads. So what you can see actually here is that the analog, requires, of course, much lower communication rounds to achieve, say, the target loss, right? Compared to the other baselines, you can actually even see that even if I give 10 times more subcarriers or channels to the digital approach, right, it actually fails to reach the same speed compared to the analog counterpart, right? So this is actually very, very, very interesting observation. Then, of course, the other baselines are actually even doing much poorer. Now, in terms of energy efficiency, you can see actually for the range of SNR value that we cover here, right? We went down to even -10 to 35. You can see that the analog case actually, provides a much lower loss at a much lower signal to noise ratio, and this is very desirable, for instance, for IoT devices in the case of low power and low SNR regimes. So again, this is very, very encouraging, and you can see actually now you need really to double the number of channels that you give to the digital solution to 200K to just see this crossing point here where the digital approach start to outperform the analog approach, right? But other than that, the analog is really outperforming it across all the ranges of SNRs. Okay, so actually this is to say that this analog federated ADMM is much more energy efficient and also bandwidth efficient. So you're gonna gain in both categories. Now, this is in a linear regression, and remember, in linear regression, the model actually is not very large. So now let's see what happens when we move to an image classification task where the model is much larger, and this is what we show here. This is the test accuracy versus number of communication uploads, right? And this is the same thing as before, test accuracy versus SNR, focusing on the communication energy efficiency. Okay, and again here are the same baselines as before. So what we can see here first is that the analog FDMM achieves a much higher accuracy, right, with the much minimum number of communication rounds. So in other words, again, more communication efficient than the digital counterpart, even when you give 10x more subcarriers to the digital counterpart. Okay. Then, the same observation also carries out here in terms of test accuracy versus SNR. You can see actually that the in order to reach the same level as the analog, you need really to increase the number of channels significantly before you can start to reach the same accuracy as the analog federated ADMM. Okay, so this is a very encouraging, in fact, result. It shows that by leveraging this channel superposition in the uplink, instead of treating the the transmission orthogonally as done in the digital case, we can significantly provide much better accuracy, right, bandwidth efficiency, and even energy efficiency. So it's kind of mind-boggling to some extent, because what we typically do is we, of course, either allocate orthogonal allocation in the uplink, or maybe try to work around that using scheduling But maybe what we should also look at is the possibility to use this analog transmission, because at the end of the day, we are in a federated learning setting where the goal is to find the average model, not the individual models of every work. All right, very good. So now in the next set of slides, we will now move to the serverless case or fully distributed setting, beyond parameter server or federated learning towards fully distributed setting. And here I will cover just few techniques. I mean, there are many others, but I'll just focus on one technique we came up with, which is referred to the group ADMM. Then we'll look at its quantized version here, and then what we can also even do in terms of better communication efficiency using a technique called censoring, where the agents will not transmit their models or the quantized models at every time t, but essentially only when, for example, the innovation of the model is larger than a given threshold. Okay, and this works appeared in the Journal for Machine Learning Research and TCOM this year. All right. So I mean, the intuition is very easy in the sense that now, of course, we will get rid of the server, right? And we'll move to the totally distributed setting. So how would you do that? Essentially, the way we started is we said that instead of asking all the clients to transmit their models to the server, right, we could actually maybe just enforce a constraint where every agent will communicate only with its most immediate neighbors. So essentially, this is how we started with this framework, right? And the idea here is that now we would have a set of neighbors, neighbors, or a set of workers rather, which would divide in terms of say head group and tail group, right? So the head group will includes the head indices here of the workers, and likewise for the tail group. And now actually what we do is that every head device will update its primal variables, right, in parallel, right? And then each head device will transmit the weights to its two immediate neighbors, so in the tail group, right? So if you take this is the head device, it transmits its model to two neighboring devices in the tail group, okay? And then consequently, the tail devices will update their primal variables in parallel, and then each tail device will now transmit likewise its model, like you can see here, the yellow here to its neighboring devices in the head group. This is essentially how the algorithm works. So it's much more communication efficient, obviously, because here every agent will communicate only locally with its most immediate neighbor, right? Instead of all the devices communicating with the parameter server. The only thing we need to ensure, of course, here is, because we are training at the end of the day one global model, we need to ensure essentially that this constraint is actually satisfied. Otherwise, it diverges. Okay, so let us see how. So here is the mathematical formulation. This is augmented Lagrangian of the optimization problem. So here, the only addition here compared to the typical Lagrangian is this term here, which is here we have the quadratic term here. This is the rho is the disagreement penalty, which will be important in the result, as we will see before. Then the primal variables of the head workers are given as follows. So every worker in the head group has to solve this problem locally, which depends actually on its own dual variable and then the neighboring models, right? Plus this term here to again highlight the disagreement between the model that the head worker has and its neighbors from the tail group. And then subsequently, the tail worker will also update their primal variables in the same way, right? So this is actually the same equation as the for the primal variable of the head workers. And then finally, locally every worker will update its dual variable lambda here, right? Without incurring any communication here. Okay, so essentially these are the steps. Now, in terms of numerical results, so here what we will compare, we plot the objective error as the number of iterations for a number of baselines. So here we considered, very recent baselines. This appeared in the NeurIPS 2019, if I believe. This is referred to as a lazily aggregated gradient. in which the client here uploads its model only upon a given threshold. Yeah, so the first version here is when the parameter server actually schedules these communicating workers. This is where the workers communicate actually autonomously. And then there's some other baselines such as the gradient batch gradient descent, and then the decentralized gradient descent. So what we can actually see here is actually the GAD-MEM, which is our proposed idea, is actually significantly has significantly lower error compared to all the other baselines actually, right? So I mean, this is obviously seen here in terms of number of iterations, and the reason for that essentially is that now again the worker is communicating with only two neighbors as opposed to all the clients transmitting their models to the parameter server. Okay. Now, even when you plot now the objective error versus the, in terms of cumulative communication costs, you can see here, that again, you have very low error compared to the gradient descent and then the lazily aggregated gradient descent for both parameter server and worker. But what's interesting for us here is to pay attention to is the impact of the penalty disagreement here, or the consensus penalty rule, right? As you can see, it has kind of a fairly important impact here, which this is to say actually is when the workers have a disagreement and do not reach consensus on the model. Essentially, this is where you have to add this penalty rho here, right? As we saw in the formulation of the augmented Lagrangian, right? And this has actually to be kind of fine-tuned as part of the hyperparameters. So the optimization of rho here is very, very important, right? And it can be, of course, further optimized. Okay. So now, in terms of, if you put this in the context of, say, IoT devices, right, and compare with the parameter server with this GAD-MEM, you would definitely choose the case where the IoT devices talk to their immediate neighbors, right, instead of transmitting, with large transmit power on the uplink to the server, which may be far away, or even if it's close, maybe there is fading on the channel. Whereas if you just communicate with your immediate neighbors, that actually has much better communication and bandwidth and energy efficiency results. All right, now let us move to the model quantization. So again, here the idea is we are trying to improve the communication efficiency. So we first said that we wanted to, avoid transmitting as in federated learning to the server, but now we would say, okay, let's transmit only among neighbors, right? Now we can even go further than that. We can say, okay, now instead of the workers transmitting their entire models to their immediate neighbors, what if we can actually quantize that model? And instead of transmitting the full precision of the model, we can actually transmit a quantized version of that. So that's essentially what we've done in this new technique called the QGAD-MEM for GAD-MEM plus quantization, right? So here the idea is actually the same, right? We have groups. We divide the workers in groups, head and tail, right? And then still, we still apply the same machinery of ADMM among the groups, updating the primal and the dual. But here we have to pay attention, because essentially, if we apply this stochastic quantization to quantize our models, there will be errors which will actually come from the quantization procedure, right? And this error will propagate among the workers, which of course will hurt the performance, but also will not allow the algorithm to converge. So in order to address that, what we actually propose is that we actually, instead of quantizing the model, we would actually quantize as you can see here, we can quantize the difference between each model parameter current and previous value. Okay, this is what is actually shown here, right? By this quantity here, which actually depends on delta here. Delta is this is the steps. This is the granularity of the quantization, as you can see here, right? And RK, this is kind of a positive term here that is added, right? And yeah, B is the number of bits, right? Theta is the model. This is the estimated previous model. So essentially, this is what we do. We quantize this difference, okay, stochastically, which means that we actually say that this value here is actually going to be rounded up with probability pk here, and rounded down with the probability 1 minus p. Okay, so this is basically the idea, and we do so because we wanted the expectation of the quantization error goes to zero asymptotically. This is the reason for that. And of course, we need to choose now, of course, what are how many bits we need to quantize our model, such that the quantization step size will actually be non-increasing. So this delta here, the quantization step size, has to be non-increasing over iteration. Okay, so this is actually what is actually shown here pictorially. All right. So now let us take a look at some simulations here. This is a linear regression setting, and with a convex loss function. The baselines are the non-quantized GAD-MEM, gradient descent, and quantized gradient descent, which is another very popular baseline. We again plot the loss here, and then versus the number of communication rounds. Here we consider actually GD, quantized GD with 2 bits, GAD-MEM, and quantized GAD-MEM with 2 bits, right? And so you can actually here you can see that in terms of communication, in terms of conversion speed, there's a significant gains versus, for instance, this quantized gradient descent. Maybe what's more interesting actually is that in the right hand side here, where we plot the loss versus the total number of transmitted bits, right? For this baseline, you can see that actually, quantized GAD-MEM here has a much lower loss. So for instance, to achieve a 10 to the minus 5 objective error here, I mean, you require much less number of transmitted bits versus, for example, a GAD-MEM here, or even GD, right? Gradient descent here, or quantized GT. Okay, and of course this could be still further optimized, because it again depends on number of hyperparameters here. Okay.
And of course, we can actually extend the current framework going from the chain topology, which you can see on the left-hand side, toward more arbitrary topologies. For instance, here in the middle, what you can see is a bipartite graph where one node in one group, here, for example, the purple group, can communicate with any number of neighboring nodes from the other group. Okay, this is what we refer to as the generalized GAD-MEM. And of course, now you could also think about leveraging time diversity in the sense that now models, that do not have to be transmitted by all nodes at every time t, but rather every node will essentially apply a censoring strategy where it will communicate the model updates only if it's above a given threshold. Okay, and this is what we refer to as a CQ-GG-ADMM. Now, in terms of result, what you can see here, this is again a linear regression task where we compare this different family of algorithms ranging from the GAD-MEM to the generalized GAD-MEM over a bipartite graph, and also the idea of leveraging censoring and quantization on top of that. And as you can see, we can actually compound some of these gains, for instance, in the case of communicating much less number of bits at a much lower number of communication rounds as opposed to the GAD-MEM, for example. So this brings me to the end of the talk. So essentially, what's next? So one of the key aspects that deserve more research, one of them is, of course, robustness. How do you learn across multiple tasks and multiple environments? Few-shot learning, the ability to learn with very few data samples, and the ability to leverage also what has been acquired, as for example, using meta-learning or learning to learn. Energy is a very much unexplored aspect of the edge AI due to our obsession with accuracy. Here we already showed that actually, if you don't take into account energy, you would be basically exploding your energy bill. Number 4, the move or the departure from statistical towards causal approaches. As we know, we always been learning basically doing curve fitting. So now we need to essentially look at causality and essentially try to model the learning as a causal graph and try to reason over this graph, instead of just learning mere and spurious correlations. This is also the 5th point, essentially to move beyond interpolation toward extrapolation outside of your training data. Essentially today we all know that we assume that the test and the training data distributions are identical. But we know that in real world this is of course an assumption which is violated, and of course much more. With this, thank you very much for inviting me to deliver this talk.